So first of all, let me thank the organizers of the workshop for inviting me to give this talk. Today, I'm going to tell you something about how to parameterize type binding models using DFT with the main purpose of performing large-scale transport simulations. So the talk is divided into two parts. Mainly, each one of them should last around 15 minutes. I'll try to be in time. In the first part, I'm going to just tell you in short some few motivations and the state-of-the-art methods for the large-scale transport simulations. And then I'm going to show you how to indeed parameterize type binding models using DFT Hamiltonians, showing you some examples related to graphene and nanoporous graphene, which is the main, which are the main materials that I've studied during my PhD at the Danish Technical University, working with Nick, for example, and Mats Brampur. So first of all, in this talk, when I say large, I mean it from the point of view of atomistic electronic structure simulations. So that means I'm not going to talk about micrometers, but already tens or hundreds of nanometers can be considered large when you simulate when you perform electronic structure simulations atom by atom. And what is interesting anyways is that the devices in experiments, they're downscaling at a very rapid pace. So they are reaching the nanoscale, and therefore being able to simulate with atomic detail, not only current voltage characteristics, but also real space quantities like currents flowing across the atoms, which make up a device, which make up the channel of a device, for example. That's becoming more and more important in order to be able to make one-on-one comparisons with the experimental measurements. And Transiesta, as most of you know, is a very nice way of performing non-equilibrium finite bias transport simulations. And that's at DFT level, density functional theory level. As you know, that's a quite accurate method. But as you also know, it's not the most cheap method from a computational point of view to simulate large-scale transport. In this figure, for example, that you see right here, let me activate the laser pointer here. So in this figure here is just an example that I like a lot of a very large Transiesta simulation made by Pedro Brandimarte, who used to work at the IPC, which is a 4-electrode Transiesta simulation, quite big, because as you can see here, it's of around the supercell is around 3 × 16 × 8 nanometer cube, and it's made up of around 36,000 orbitals. So from a Transiesta point of view, at the DFT level, this is already a quite heavy system to simulate. You can imagine, however, that there are some situations, like for example, ballistic transport in graphene systems, which need transport simulations at a much larger scale. We're talking about even way more than hundreds of nanometers. Like it was reported, for example, in this other article, which reported in the ballistic transport beyond 25 microns in graphene. So it's really becoming important to be able to simulate atom by atom this range of scales, of space scales. Just to give you an idea, a 100 by 100 nanometer square graphene sheet is made up of around 400,000 atoms. That means that if you want to simulate that by using DFT, for example, an LCAO basis set, the simplest one, like a single zeta basis, you have 4 orbitals per atom, and that amounts up to more than 1.5 million orbitals. You can easily understand that that's not really one of the easiest systems that you can simulate at the DFT level. So one often tries to find a compromise in describing the Hamiltonian in a minimal basis set so that it's both accurate and scalable. So one of the most popular and easy minimal basis sets is the type binding one that most of you, I guess, are aware of. Now, that's a very, very versatile solution to describe electronic structure. Depending on the system, of course, and on what one is interested in, one can even reach models which have only one orbital per atom that can have also a very short interaction range. And that leads, of course, to a very efficient Hamiltonian matrix. It's small in size, it's very sparse. It can also be orthogonal, depending on the system and on what you want to study. The downside, in a sense, is that it's not the most accurate model. Very often, it's not very accurate and not so transferable, because very often the elements of the Hamiltonian matrix are found by fitting the bands from DFT or another ab initio calculation for a very specific system within an energy window. But of course, there are many other different solutions, which I'm listing here. Of course, it's a non-exhaustive list of possible solutions, state-of-the-art solutions. But and I'm not going to describe all of them in details, of course. But in general, I wanted to emphasize that most of the possibilities for representing the electronic structure of a system with a minimal type binding basis sets can be categorized into types, more or less. And one of them needs is based on an explicit calculation of the Hamiltonian elements using fixed localized functions, and that's the case, for example, of siesta itself. It's a linear combination of atomic orbitals, and so already with respect to plane waves DFT codes, it's quite more scalable. But there are a few other methods which were developed also more recently. One of them is the Vanier methodology, but also projection onto pseudoatomic orbitals, or even more recently, actually very recently found this article, where type binding models are built in an iterative way using machine learning algorithms, which are indeed based on sort of downfolding the DFT Hamiltonian into a smaller Hamiltonian, which reproduces only a few hand-picked bands within an energy window that you're interested in. Now, this can be more or less, the latter category can be more or less summarized with this very simple formula, where on the left side you have, on the right side you have this basis set filled with alpha, which can represent, for example, which usually represents a DFT basis set coming from an LCIO calculation or a plane wave calculation. And on the left side, you have a smaller basis, which indeed reproduces some bands of interest, and which has been obtained by applying to the original basis set some kind of projection operator, which can be more or less sophisticated depending on the approach you use. So what you can do in CISL very easily, very quickly, in basically one line of code, is to use this formula in the simplest possible case, which consists in simply selecting a subset of the original DFT basis functions that you obtain, for example, with siesta. And that you can do with this command. That's basically the main thing I'm going to talk about in this talk, and the only command that I'm going to describe, because it's seriously just all about this command. You'll see how to use this in the hands-on tutorial after my talk, more in detail, of course. But let me give you a little bit of hints on how it works. Suppose to consider, for example, this graphene usual lattice that you've seen also in the other tutorials that you've made yesterday. Now, and consider the primitive cell, so the one made of 2 atoms. If you simulate that with DFT with a single zeta basis, which is actually the simplest one you can use in siesta to describe carbon atoms, you have 4 orbitals per atoms. In the unit cell, you have 2 atoms. So the Hamiltonian matrix, if you use, for example, IMSHO in Python to just plot it, the color bar, at the gamma point, you get something like this, okay, where green is just zeros and the non-green is some elements. Now, as you can see, you have an 8x8 matrix in this case. What you can do with suborbital is to, for example, select only the PZ orbitals, and in particular the rows and the columns associated to PZ orbitals in the system, and get a smaller matrix, which is indeed made only of the on-site and couplings between these specific orbitals. The same thing you can do, for example, with other orbitals, not just PZ. You can do it with the S, Px, and Py, for example, and then you would get a 6x6 matrix for the gamma point, which looks like this. So in this sense, suborbital is really subbing, taking just a subset, a sub-matrix of the DFT Hamiltonian matrix. Now, this, of course, is only for the gamma point. Let's say for the 000 supercell that you get in CSUL when you construct an Hamiltonian. Of course, that's valid also for the other K points. So at the end of the day, what you do with this command is to get a smaller Hamiltonian, which preserves all supercell connections that you had in DFT. Therefore, it preserves the full interaction range between orbitals, between the orbitals you've selected in DFT. And important, if the original basis set was non-orthogonal, like in the case of the siesta calculation, the final Hamiltonian will also be non-orthogonal. So let's see, for example, what happens if you plot the band structure of this big DFT system and of the two of the two projected Hamiltonians. As you know, graphene has two different sets of bands. You can divide them into sigma bands and into pi bands. The pi bands are, as you can see in this band structure plot, I've also plotted the orbital weight on each of the eigenvalues. And in particular, in blue, you see the contribution from the PZ orbital. In red, you see the contribution from the S, Px, and Py orbitals. You can also see some other gray areas. That's because the original basis set in DFT was a single zeta polarized. So you also have polarization orbitals, which give some contributions in the unoccupied bands. This is the so-called fat bands analysis of the band structure. Now, this is for the single zeta polarized calculation. When you use the command suborbital to get the smaller Hamiltonian, you can actually manage to get two separate Hamiltonians which reproduce, in one case, when you project only on PZ, the pi bands, and when you project instead on the S, Px, and Py, the sigma bands. Now that's pretty easy for graphene, indeed, as you already know how the band structure looks. Importantly, I wanted to emphasize here that the importance of the interaction range. As you can see, if you were to preserve from the DFT Hamiltonian only coupling elements up to certain nearest neighbor, which is not the largest, the farthest nearest neighbor that you can consider in DFT, then the bands would not be reproduced. Another thing which is important is that compared to a regular first nearest neighbor tight binding model for graphene, the one with the hopping 2.7 EV, for example, you can see that more or less around the Fermi level, it's well reproduced. The bands are well reproduced, but far from it, far from the Fermi level, there are some distortions. So extracting the Hamiltonian from a DFT calculation rather than by using this the semi-empirical tight binding model for graphene adds some more accuracy to the bands. So you'll actually do exactly these kind of plots in the hands-on session that you'll do after my talk. And also you will have the chance to try and use this command to make lighter Hamiltonians for other types of materials, for example, like 2D materials like HBN or MOS2 or whatever you like, of course. And now let me just give you one more example on how to parameterize tight binding models with DFT for another system, which is a system we've been studying a lot in the last few years. This is nanoporous graphene. It's, as you can see, just graphene with some very small holes, nano-sized holes. It's a very interesting system. It has been synthesized bottom up and published in and reported in Science just a couple of years ago. And what you can see, the peculiarity of this material, besides making graphene a semiconductor, so making it more useful for making devices, indeed, the anisotropy in the holes, so in its structure, leads to an anisotropy in the bands. This is the typical band structure for such a system, and you can see that depending on the energy range, you have an energy range where the bands are mostly dispersed along the gamma y direction, which is the ribbon direction. And in some other energy ranges, instead, it's highly dispersive along gamma x and basically flat bands along the y direction. Now that allows us to distinguish two very different regimes of transport in this material, and this can have some consequence on how currents flow very far from in the far field, so over long distances. I'll maybe show you something about this in the second part of the talk. And so this is always the same story. What we did was to perform a fat bands analysis on this material. We were able to see that most of the longitudinal bands have contributions from the PZ orbital. And furthermore, you can see that you can see in the middle plot that by extracting indeed the PZ Hamiltonian from this single zeta polarized one, you can get a qualitatively good band structure. You have to look at the dashed one. As you can see, the only difference with the DFT, the main difference with the DFT is an energy shift, which is, however, a rigid energy shift. And that's basically due to the fact that by extracting only PZ from the Hamiltonian, we are neglecting some orbitals which have also some symmetries along the z-axis, and that could therefore hybridize with the PZ orbital and give rise to slightly different alignment of the bands. As you can see on the right side, for example, by including the polarization dy z and pdxz orbitals, you can actually retrieve the bands, the DFT bands, quite well. So another interesting thing that you can, for which parametrizing a tight binding model with DFT is crucial and fundamental, is actually in the case of studying a gated system. As you know, in Siesta, you can apply a gate to your system. So you can electrostatically gate it in order to populate or depopulate the bands. And in the case of simple nanopore graphene, the one that was actually synthesized in the Science paper, but as in graphene, as in regular graphene, the application of an electrostatic gate simply shifts the bands up and down. As you see here, this is the zero gated case. This is the n-doped case and the p-doped case. What you can see is that you can also simulate these gated systems quite well by extracting the PZ. But and indeed, this is kind of the same as just shifting rigidly the bands. There are some cases, however, where a gate cannot be simply modeled as an on-site shift of the on-site elements of the Hamiltonian. This is, for example, a band structure evolution as a function of the gate voltage applied for a functionalized type of nanoporous graphene that we are studying these few months, in the last few months. And what you can see in this case, the band structure is spin polarized, the system is spin polarized, and the presence of these localized states close to the Fermi level causes a non-trivial population of the bands. Therefore, as you apply a gate, the bands are not simply rigidly shifted, but they are distorted, they are mixed, they are entangled. And therefore, and as you can see in the right side, in the rightmost panel, by using this DFT-based parametrization of a tight binding model, you can capture this entanglement between bands. this is the last slide before this short break, just to show you that by indeed projecting the Hamiltonian onto a subset of its orbitals, especially for these simple carbon systems, you can get a way more accurate description of the potential map in the structure. As you can see here, since there are some edge carbon atoms around the holes, you can capture the potential difference between the carbon atoms in the middle of the ribbons and the other ones around the edges of the holes. And in addition to this, if you were, for example, to put a gold tip in chemical contact with the system, this would cause end doping. And you could see by parametrizing the PZ or the system only onto PZ, you could see the distortion, the perturbation to the PZ energy around the contact point. So this is quite interesting and useful if you want to study perturbations. Perturbations also like defects, as in this case of an epoxy on graphene. I will show you something about this in the second part of the talk. But also if you want to study distorted system, if you consider, for example, the MPG, the nanoporous graphene again, you can actually reproduce the DFT bands not only for a flat system, but also for a distorted out-of-plane system, simply by adding the sigma orbitals to the final Hamiltonian. Apart from this rigid energy shift that I mentioned before. So just in conclusion, to give you the take-home message, CISL is nice because it allows you to project a DFT, in particular a linear combination of atomic orbital basis set onto a subset of its orbitals, thus reducing the Hamiltonian size. And all of this you can do it in one line of code, basically. Now, this has the advantage of being a direct projection. You don't need any iterative optimization, no bands fitting. And by doing this, you're also able to capture some basic perturbations, like perturbations to electrostatics or to the structural geometry. And if you're asking yourself whether you can apply this to your system, then the answer is simply just do a fat bands analysis, study the orbital contribution to the bands, and see whether you can do that. And so I think now we can take a small break. Second part will hopefully be a bit faster.
Gaetano, we have the 2 questions. Maybe you can have a look at them in the Q&A.
Yes. So Dongji asks, what is the general strategy to select the targeted orbitals for the projection? For instance, if we want to model some more complex systems than graphene. And so the answer to that is indeed what I just said, which is do a fat bands analysis, analyze the orbital contribution to the bands, and see whether the bands you're interested in reproducing have contributions from a limited amount of orbitals. And if yes, then most likely using this command will do what you want. And Alexandre instead is asking, the Hamiltonian generated by CISL, there's a way to print the matrix element in a way to use this tight binding model for other purposes. Well, if you mean to print it to a file, then I guess the simplest way is to store it in a netcdf file, as you've seen in the exercises from yesterday, for example, and then just read it and use it for something else. That's the easiest one, but there's different input output options. It's easy to do that. You can check the documentation probably. So Christian from EPFL is asking, very nice. Thank you. Could you please repeat the part about the applied gate voltage? Is that a parameter that one can set in the Transiesta calculation? So I actually didn't talk about how to apply a gate in the Siesta calculation, because that's more related to Siesta. Indeed, you can just check out the section on electrostatic gating in the Siesta users guide to understand how to do that. There are different ways of doing that. You can either apply a charge on a plane at a certain distance from your system, and that would induce a charge on your system. This is for the case of 2D materials, for example. Or you can directly charge the system. You can put a charge inside the system and simulate doping like that, for example. But I suggest you check out the manual from Siesta. Constantine is asking, can you please give a few more examples of the systems to be successfully described by DFT type binding, something more complicated than graphene, half metals, transition metals, where plasma is typically used? So that's actually a good question. I've not studied so far systems different from graphene and nanoporous graphene. To be honest, that's one of the things that I mean, you need to check for yourself depending on what system you want to study. I can't really tell you now a general rule or what you need to do apart from analyzing the fat bands plot for the system you're studying. In a sense, I mean, there are in case the suborbital command doesn't work, there might be some other ways of maybe exploiting the sub Hamiltonians, the reduced Hamiltonians, to combine them somehow using more sophisticated methods inspired from, for example, from the projection onto pseudoatomic orbitals or Bannier functions. But yeah, there's I don't really have other examples on other materials so far, at least. Then Guido is asking, in modeling two top contacts in Transiesta, since the initial calculations adopts periodic boundaries, one is practically putting a finite, not periodic device with cut contacts separated by a suitable vacuum region before applying the electrode self-energy. So I'm not really sure about what you're referring to, maybe to the simulation that I've shown in the introduction that had two top contacts. But I've not performed that calculation myself, so I don't really know the tiniest details of that. I've put a reference in the introduction slide just to, if you want to know more about that. I think in the supplementary material of that article, of that Nature Communication article, there's a lot about how the simulation was performed in Transiesta.
Maybe I can jump in.
And yeah, just do it.
So this calculation that Pedro did with the 4 contacts, on the back side of the 2 top contacts, there are buffer atoms to screen off the vacuum. So you still have the screening effect of some periodicity along the bulk direction of the electrode. So that exactly these kind of calculations is where buffer atoms are extremely useful.
Thanks, Nick. And then the last question here is from Xavier. Can you choose to project on an orbital, let's say S for a particular chemical species, and on a different orbital, say PZ, for another chemical species on the same system? That's a very interesting question, and the answer is yes, of course you can do that. You'll see actually, you can try by yourself in the hands-on session. There's an exercise about that. For example, when you try to make a projected Hamiltonian for HBN, for example, or for MOS2, well, the basis sets are different for the 2 chemical species. You have the chance there. You need to select different orbitals on different chemical species in that case, for example. So you can do that just by applying sequentially the suborbital command. There's another question. If the defects are transition metal impurities where U assumes importance, can this parametrization be used by adding the impurity Hamiltonian, like Anderson Hamiltonian, to the type binding Hamiltonian? Could you comment on that? Well, that's actually an interesting thing to try. I don't really know how you apply the U correction to the Hamiltonian, if that's just a simple, that because I'm not experienced in that. I think there will be some talks about this in the workshop, right? On the Hubbard approximation and how to study that in CSOL and TP tracks. But I mean, as long as you, I mean, once again, I think the most important thing is that you check the bands and the contributions to the bands. I mean, if you do the simulation with the U for the DFT system, and then you analyze the bands and the contributions from orbitals to that band structure, if you see that there are some well-defined contributions for some bands, then I guess there's no problem in just taking this, using this parametrization technique. But you should, it's just an assumption. I'm not really sure about that. We should try.